So on Friday, I mentioned that this is our confidence interval for dealing with a proportion. And notice that there's a z-score. If there's a z-score, we're assuming that we have a normal population, that we have a normal distribution. Otherwise, we need to use a t-table, and our distribution for that then depends on our sample size. Now, normally, typically, how do I make the assumption on being normal? I need to look at my sample size. So our assumption that our population is normal needs to be justified somehow. We need to know how big a sample we need to take. Normally, remember that our proportion is determined by the number of things we want versus our sample size. I need to know that I've done enough not to be biased in favor of results that went the way we want or results that went against us. So I need, or at least I want, at least 10 successes and at least 10 failures in order to make this work properly. Problem. This depends on our proportion. So if our population proportion, because remember, we're looking for the population, we're using P as an estimator of it. The further away that is from a half, the larger our sample size is going to need to be. If something has a 1 in 1,000 chance of happening, and I want at least 10 times where it happened, I need 10,000 samples. If something has 1 in 1,000,000 chance of happening, and I won't see it at least 10 times, I need to do 10 million samples. That might not be possible. The further away our proportion is from 50-50, the more samples we need. Now, we are not often in a case where we are looking at extra rare events like this all the time. And on page 294, there's a table. Notice that when we are 50-50, well, then I only need 20 samples. But as our proportion gets further away from 50%, in either direction, smaller or larger, these numbers grow. And like I said, if you have a 1 in 1,000 chance of something happening, or a 1 in 1,000 chance that it doesn't happen, you need 10,000 samples to make an assumption of your population being normal. So I can't always make this assumption. But when I can then use this formula. And this formula uses the z-score from our normal distribution. the smallest possible sample size we can have comes when this proportion is 50%. So when I look up at this estimator and I say, oh, my confidence interval is breaking around this proportion P, this estimator, alpha is our confidence level. N is our sample size. And I can think of this entire term as how far off I think I am. Here's my estimator, give or take some. Mike, what did you call that on Friday? Aha! So we can think of a margin of error this way. Well, I either have to lose confidence to make that interval narrower by making Z smaller, or I have to up my sample size. It's almost always easier to up the sample size and keep the confidence the same. Normally, typically, we try and aim for a 95% confidence. If I'm doing a 95% confidence, then our alpha is the leftover. So I need Z of 0.025. Wait a minute, I know that number. We used that number a bunch. Grab your table. Look on your note card, your formula page. Bunch, you wrote this down already. What's Z of 0.005? Sorry, 0.025. Got to write down the right number. That is our 1.96. And the smallest possible sample occurs when our proportion is 0.5. So I could ask the question, using these two assumptions, what N do I need? How many people do I need for a particular margin of error? Well, remember that entire term inside the parentheses, that entire term, that's my margin of error. So let's take that and solve for N. Margin of error equals Z alpha over 2 square root P1 minus P over N. But I'm making two assumptions, aren't I? I'm making the assumption that I'm doing a 95% confidence interval and that my smallest sample size occurs when P is 0.5, which really means I can put the 1.96 here. And I can put 0.5 in for P. Oh, I wrote P, that should be a 0.5. Wait a minute. 1 minus 0.5 is also 0.5, isn't it? So this is 0.5 times 0.5 on the top. Rearrange that equation. Solve for n. Want to solve for n, I got to get rid of the square root. So let's square both sides. And now I put the n over here by multiplying, and I divide by the margin of error squared. And then I notice everything in that fraction is squared. If everything is squared, I can pull that square outside. So if I tell you that I want you to give me a 3% margin of error, how many people do we need to ask our question? Minimum. Three percent is 0.03. So you calculate on the inside, 1.96 times 0.5 divided by 0.03. Square that answer. At least 1,067 people. I don't know how many of you paid attention to the polls last November before the presidential election, but almost all presidential polls are conducted with a 3% margin of error, which means when they're figuring out how the country is going to vote, they're asking 1,100 people. Out of 360 million people in this country, about 2/3 of which are registered voters, that's 240 million people. They asked 1,100. And that's why the margin of error is 3%. And they can do this poll so often because it's only 1,100 people. Now, there are lots of other sources of error. We could have bias in our responses. We could have overcorrections trying to adjust to the population accordingly. There was a very famous painting of Harry S. Truman, a photograph of Harry S. Truman holding up the headline of the paper the morning after the election. It says, "Dewey beats Truman." Do you know why the newspapers were so convinced Dewey was going to beat Truman? Dewey was a Republican, Truman was a Democrat. Why were they convinced Dewey was going to win? And when is Harry S. Truman president? The internet is your friend. When was Harry S. Truman president? And that meant phones were not very common, and you had to be fairly well off to have a phone. And if you were fairly well off, you were probably voting in the Republican direction, not the Democrat direction. They had bias in their sample that they didn't even realize they had. As we try and go back and forth to adjust for other possible sources of error, we end up potentially changing that margin of error quite a bit. Question? So there's a very real way to build margin of error out of our assumptions about a proportion. It's not as easy to do for a mean, but it is fairly direct for a proportion. If I tell you how many people we did the survey of, you should be able to compute a margin of error. We did 250 people. What's our margin of error? Aha. So in this case, I know n. I'm going to use this version of the formula right here. Margin of error is the square root. Sorry, it's 1.96 on the outside of the square root. 0.5 squared over n, 250. And you said that was 1.96 times the square root 0.5 squared divided, whoop, came out of this square root. Let's go back in the square root, divided by 250. There we go. Right, okay. 0.062, 6.2%. So 250 is not going to give me a very accurate survey for a proportion. Questions? Note the 0.5 is squared and then under a square root. So it's also possible to write this margin of error calculation as 1.96 times 0.5 without the square root and just put the square root on the bottom. Because when you take a square root of something squared, the square root and the square cancel each other out. This should end up on your formula sheet. So the first deal we had to look at is our population normally distributed? If it isn't, then we can up our sample size to make some adjustments to reduce our error. But what if our population itself is small? This is a term we used back in chapter 2, where we talked about a population being effectively infinite. And our sample size was less than 5% of the population. So if when we sample, we're using more than 5% of the population, then really we have a finite population size. And then I have to correct my confidence interval, because it's possible with a finite population that your samples are getting much more of stuff further out just by happenstance. So I need to figure out how to make my margin of error smaller. And the way to do that is something called a finite population control factor. And this is just a number that takes into account the relative size of our population versus our sample. As a matter of fact, this number is always smaller than 1. So when I multiply that into our margin of error, it's going to make our margin of error smaller. So here's a way to control my margin of error a little bit better when my population is finite by comparison to the size of my population. Notice there are 3 formulas on page 299. All 3 of those formulas are exactly the same as the formulas we've already used. If I'm estimating a mean and I know the population standard deviation, this is the formula I use at the top here. Take your sample mean, then add or subtract Z alpha over 2, that's our confidence level number, times standard error. But now I'm just going to multiply on the finite population factor. This is what happens when I don't know the standard deviation for the population. I use my sample standard deviation, but then I have to use a t table, not a z table, because we're dealing with the weirder distribution. And then I multiply by this control factor. Same thing with a proportion. So all I have to do is multiply this onto my margin of error to take into account the relative size of the population. So let's consider we have a sample mean of 50. This is problem number 39. A sample mean of 50. A standard deviation from the population of 15. A sample of 90 out of a population of 1,000. First question. Is this population effectively infinite for this sample? Why not, Max?
Below 5%.
Aha. 90 divided by 1,000 is 0.09, which is bigger than 0.05. So this is a finite population. So if I want a 95% confidence interval, the 5% confidence interval for the mean. I need to know 2 things. First, which of the 3 formulas that I just showed you are we going to use? The first one, because we know the sample standard, the population standard deviation, exactly that. Because that's a sigma, not an S. So I can use that first formula. So I take the average I was given, add or subtract Z alpha over 2 times the standard error. But since this is not an infinite population, I need my control factor. My average was 50. My standard deviation was 15. My population, sorry, my sample was 90. My population was 1,000. What goes here? That's exactly right. Because we're doing a 95% confidence interval, we use that Z of alpha over 2, and that is 1.96. That's even the one that's circled. 0.4750 is circled in our table. Okay, this is just an extra decimal to multiply in. 50 plus or minus 1.96. 15 over root 90, then the square root of 910 over 999. Out comes my calculator. Let's compute our margin of error. I'm literally just typing in those three fractions, those three numbers in order. 1.96 times 15 over the square root of 90 times square root of 910 over 999. I'll call it 2.96. So when I add, I get 52.96. That's my upper bound. What's my lower bound? Well, given where I rounded, I would write 0.4, but if you kept more decimals, you might end up at 0.3. Absolutely. Since I rounded here. Hey, even with only 90 people sampled, my margin of error is 3%. Remember, this was for a mean, not for a proportion, so it changes things. I should be able to do the same sample size idea that we did for a proportion, to do a sample size for a mean with a given margin of error. Even in the infinite population case, I still should be able to do this same idea. So let's think about this idea. If I have an effectively infinite population, then My formula looks like that. I just realized I wrote those last two terms backwards, but they're being multiplied, so it doesn't really matter what order I put them in. I normally put the Z first. I apologize. I started to write sigma before I could stop myself. I have to use this formula. I can't use the other formula. Why can't I use the formula that involves T? I promise there's a real reason for it. Promise there's a reason. How do we figure out what T value we're going to use from our table? I need degrees of freedom, which requires N, and I don't know N since I'm trying to figure out N. I'm trying to find N. Degrees of freedom are based on N. Oops. So I have to use the Z formula. But then my margin of error should be this part. That's the part that I'm adding or subtracting to my estimator. That's my margin of error. That's my margin of error. I should be able to solve for N given a fixed margin of error. Well, I'll just swap the places first. Root N is Z alpha over 2 times sigma over the margin of error. Then I got to get rid of the square root. So I square. This looks very similar to our previous one, except we had 0.5 and 1.96 fixed for us because we are given the maximum possible confidence interval size idea. Even if I assumed I was going to do 1.96, this works for all possible setups for whatever confidence interval we're looking at. But now I have a problem. It's not a huge problem, but it is a problem using this. In order to use this formula, I need sigma. And I don't necessarily know sigma at this point in time. I don't know my population standard deviation. How do I get this? Another question is, how can I try to get my standard deviation? I have to make some assumptions. Or I have to estimate. How do we estimate? We had an estimator for sigma. What was the estimator for sigma? The estimator for the population standard deviation is what is our estimator for population standard deviation? The estimator for sigma is the sample standard deviation S. So I could do a sample to try and figure out how many people to sample, and this seems really freaking stupid. I don't like this idea because I would do a sample in order to figure out how to do a sample. That's just weird. So what I could do instead to try and figure out my standard deviation is I could make some assumptions about the population and its distribution. Now, since we're dealing with sampling, we really want to work with our continuous distribution. That means we really only have two to pick from. We can either look at uniform distribution or a normal distribution. So if I assume it's uniform, then I can go back to chapter 7 and I can ask, what's the standard deviation for a uniform distribution? It's that. And that formula is right out of the textbook, right out of our notes on uniform distribution in chapter 6. But wait a second. What are A and B? Exactly. So if I know what the high and the low are out of my distribution, what's B? That's the biggest possible value. What's A? It's the smallest possible value. Now, if I'm going to estimate the high and the low, well, you could be saying, okay, let's suppose we're doing, I don't know, high jump, track and field competition. I'm pretty sure that most of my competitors can jump at least 1.5 meters. The world record is less than 3 meters. I could use those two numbers right there. I estimated high and low right away. I'm estimating times on running a 400-meter dash, quarter mile. What's the estimated time on a quarter mile? Oh, I can look at historical records, and I can make an estimate for the high and the low. I can estimate my standard deviation. But that assumes that my distribution is uniform. What if I assumed it was normal? Then I know that the high and the low, 99.7% of the data is no more than 3 standard deviations up and 3 standard deviations down. If I'm estimating the high and the low, I can just say it's 6 standard deviations from the high to the low. And then I have a definition for the standard deviation. It is possible that this is actually going to be too small, because there is a chance that you have unusual outliers, data outside the 3rd standard deviation in either direction. If you have outliers in your data, then this will be a bad estimate, and we'll need to adjust it somehow. Maybe we'll go out to the 4th standard deviation instead and use 8 on the bottom. But that would assume that we have some really high and some really low numbers involved here. There are other statistical assumptions based on other types of distributions, but we only covered uniform and normal. There's the Poisson distribution, the exponential distribution, the hypergeometric distribution, a triangular distribution. There are all sorts of other distributions, but we didn't cover them. These work in 99% of the cases. And now that I have an estimate for sigma, you can give me a margin of error. The margin of error for a mean is in different units than the margin of error for a proportion. The margin of error for pi was a percentage. I said we were estimating a proportion. A proportion is a percentage. What percent of the people have this opinion, did this thing? I can use a proportion, that's a percent. But if I'm looking at that high jump idea, or the time on the 400 meters, well then, if I'm looking at the high jump, I should probably be using a margin of error of centimeters. I should probably be using a margin of error for the 400 meters in seconds. So my units for a mean and a standard deviation change my units for margin of error. So just listen to the setup of the problem here on page 302. Here are a couple problems. Problem number 43. Last year, a study showed the average task withdrawal took 65 seconds with a standard deviation of 10 seconds. My margin of error would be plus or minus 4 seconds in this problem. 45. Popcorn kernels are believed to take between 100 and 200 seconds to pop in a particular microwave. What is the estimate for the true mean to pop with error plus or minus 5 seconds? I got to use the same units I'm using up here. Mean spending per customer at a restaurant, 95% confidence, an estimate of 25 cents. I'm estimating in dollars and cents because I'm looking at customer expenditures. I have to check my units here. When I am doing a proportion, the margin of error can come from my sample proportion. If I don't have one, I'm going to have to do an estimate for that. I can make the assumption it was 50%. That's what we did for our numbers, because that gives us the smallest possible population to get a particular margin of error. But I could also look at historical data and say, hey, historically, like on the question on the exam, 30% of customers order a light beer. My P is 0.3. I have that information in front of me. Now I can estimate. If I have, again, the option to do a preliminary sample. I said I didn't like this. Why do a sample to tell you how many people you're going to sample? It seems kind of redundant. But all of this same idea results in a calculation. Z squared. Hey, there's our P minus 1 over P. Same formula we just used. We just made the assumption P was 50% and went from there. You can do it more generally. Why do I care about figuring the sample size before I do the survey? Question, how do I answer that? Who gives up? Why do I care about how many people you're going to survey?
See how expensive it would be and how accurate you're gonna be.
I think both of those are pretty good, Max. I expect this is not a cheap process, right? You're going to go back and audit the book for that restaurant for the last month if you need that many samples. Or maybe it's just a day, but then you're paying an auditor to do this job. And that could be, for compliance issues, a very expensive proposition. The EPA auditors take weeks to audit plants for compliance with environmental regulations. So this is not a cheap idea. Figuring out how big the sample needs to be in advance helps me up front inform my decision on my choice of confidence interval. I could say, oh, well, if I need to be 95% sure I need to do this many people, but to be 90% sure I only need to do this many people, and it's smaller, maybe that's a better trade-off. But these are concerns that financial managers, auditors, auditing agencies, government inspectors will have to weigh. Now, the next question comes up. The flip side of this, I did a survey. I have a sample mean. I have a sample standard deviation. I have a sample proportion. Is something wrong here or not? I need to figure out how to use the statistical information I get to ask the question, is everything okay here or not? Fraud detection comes out of the idea we are going to start on Wednesday. I will see you all then. I hope you have a wonderful rest of your day. This is the end of chapter 8. That means that homework is due on Friday.